We are going to start the week off with learning about what we call functions in math. And you're somewhat familiar with functions already because of our function machines last week as we were learning about proportional relationships. So functions act a lot like vending machines. When we have a vending machine, typically, if you've ever used one, you enter a code into the keypad and something comes out, maybe a bag of chips or a bottle of soda, but there's an input and an output, and that's what a function does for it. It takes our inputs and turns them into outputs. You can see on the screen here the formal definition of a function is a relationship where each input has one output. And here's a couple of examples of that using our vending machines. I can put in the code D4 and it gives me one option that comes out, and that would be pretzels. I can put in C2 and only one thing is going to come out, and that is a bag of chips. I wouldn't expect anything else to come out other than pretzels if I put in D4. That means for this input of D4, there is only one output option. For this input of C2, there is only one output option of chips. If I put in C2 and expected chips, then it would be really strange if out comes a can of Coke. To drive that point home, we're going to look at 3 examples. You can see that 2 of them are functions. The first 2 actually represent functions, but the third one is not a function. So if I put D4 in a vending machine, then it would give me pretzels. If I put C2, it would give me chips. That's a function because there is only one thing that comes out if I put in D4. There's only one thing that comes out if I put in C2. Over here, this is a little bit different, but it still represents a function because D3, if I put in that code, gives me pretzels. There's only one thing that will come out if I put in code D3. If I put in D4, I also get pretzels. But that's okay, as long as there's only one thing that possibly comes out if I put in code D4, and that is only pretzels. And same with C2, I will only get chips. Now moving over on this side, this is showing me if I put in D4, I get pretzels. If I put in C2, then I could get chips, or I could get a bottle of water. Now, how would that make you feel if you were hungry, you wanted a snack, you put in C2 expecting chips, but out pops a bottle of water? You would not be happy. So this, of course, is not a function. It's not okay because for this particular input, there is more than one output. In math class, we don't use vending machines, of course, to recognize our functions. We use input-output tables. So let's compare these 2 input-output tables. You can see that this first one represents a function, and the second one does not represent a function. Take a look at them on your own. Pause the video if you need to, and maybe try and figure out why. So let me remind you that an input-output table represents a function when, remember, there is only one output for each of our inputs. So let's test the first table. For my input of -1, there's only one thing that I can get as my output. That's 5. For 0, if I put a 0 in, I can only get a 3. If I put in a 1, I can only get a 4. If I put in a 2, I can only get a 7. If I put in a 3, I can only get a 4. So therefore, there is only one output for each of these inputs. Now let's go over to the second example. If I put in a 3, an input of 3, then I only get a 0. However, what if I put an input of 4? Not only can I get a 7, but I can also get an output of 14. And that is not okay because that means for the same input of 4, there are 2 possible outcomes, and that is not okay because remember, if this were a vending machine, if we put in a 4, we would expect only one item to come out, the item we were looking for. We wouldn't want to be surprised by something different. So now that we have an understanding of what a function represents, an input-output table where each input has only one output, We also can take our learning a little bit further and start to recognize graphs that represent those input-output tables. You already know that an input-output table creates a line on a graph. But the new piece of information that we want to understand today is our graphs can be linear or nonlinear. And linear, you can see that there's that word line in there. Linear simply means they make a straight line. So if you look at each one of these linear graphs, each one of these green lines are straight. They can be slanted one way or another, but all of them are straight. They don't curve. Those are linear functions. That means we would have an input-output table that would create a straight line on a graph. Now let's move over to our nonlinear. So nonlinear means they do not create a straight line. And you can see all of these examples here on the right. They are functions because they have an input-output table where one input gives only one output. But when we graph them, we can see that they're not just straight lines, they are non-linear. They make curved lines. And finally, we're going to take our learning one step farther. We also know from our proportional relationships learning that not only do our input-output tables turn into a graph, they can also be represented by equations. So I've got an input-output table represented by an equation over here on the left and over here on the right. Let's start with the one on the left. So I have taken this equation and I've taken my inputs, substitute the value into the equation, and come up with my output values. I've already done that for us just so we could go a little faster. I just want to make sure you understand where these numbers came from. So if I put in a -2 into my equation for x, my input, that would be 3 times -2, which is -6, plus 2 turned into an output of -4. Y equals -4. And that's what I did with each one of our input values and turned it into an output value. Then so once I have my table, I plotted my points. So -2, -4 was -2, -4 right here. And -1, -1 was -1, -1, this guy. So I plotted all the points, and here is what that created. It created a straight line or a linear function. So the equation that we have up here of y equals 3x plus 2 represents a linear function. And why? Because when we graph it, when we figure out the input and output values on our table and graph it, that equation represents a straight line, making it a linear function. Same over here. I'm not going to say too much about it. But when I have this equation, y equals -2x plus 4, I also can create a straight line with it. So this straight line represents y equals -2x plus 4, and therefore y equals -2x plus 4 is a linear function because it creates a straight line. So let's look really quickly at some nonlinear functions. Same thing, I have an equation at the top. I used inputs to turn into outputs by substituting them into the equation, and then I plotted them. And you can see that this equation, y equals x cubed minus 2, is not a linear function, it's a non-linear function. It did not make a straight line. Same with this guy, y equals -2x squared. It does not represent a linear function because it did not create a straight line once we graphed it. And so in conclusion, I want us to have an understanding of what types of equations are linear equations and what types of equations are non-linear equations. Let's look back at our 4 examples. So we can see that y equals 3x plus 2 was linear, y equals -2x plus 4 was linear. At some non-linear functions, and x cubed minus 2 and -2x squared were non-linear. Do you happen to notice anything that they have in common or not in common? Maybe you noticed that the linear equations involve x to the first power, or just x. The nonlinear equations involved x to a different degree, so that would be x squared, x cubed, x to the fourth power, and so on. Anything all the way up to infinity, anything that involves a degree of x squared or higher means that our line is not going to be straight. We're going to have a non-linear function.